It's recording now. It's going to record now, I think. Share screen reactions.
We have another person.
So I think we can go ahead. Once more, you're welcome for this course. I'm Professor Oliver N. Maitera. I will be taking you in chemistry 307, atomic and molecular structures and symmetry. This, our first class, will be looking at atomic and molecular structure. Is actually basically based on the electrons and the nature of electrons as they revolve around the orbit of the nucleus. Like other elementary particles, the electron is subject to the laws of quantum mechanics, and it exhibits particle-like and wave-like nature in particular. There are major objectives that we'll be looking at in this very particular course by trying to define and distinguish between shell, subshell, and orbitals. We'll also try to look at the relationship between the quantum numbers and also make comparison between them. So in chemistry, the term electronic configuration actually refers to the arrangement of electrons as they orbit around the nucleus. I am sure we are aware of the concept of the atom. The atom itself has the nucleus with the protons and the neutrons inside, and you have the electrons that are revolving around the nucleus in an orbit. The neutrons and the protons, the neutrons are actually neutral, the protons are positively charged, while the electrons are negatively charged. Now, the electrons revolve around the nucleus in orbit, or in what we call shell. From our elementary chemistry, they are called shell. You have the L shell, you have the K shell, you have the M shell, you have the N shell, and so on and so forth. Now, each of these shells has the capability of accommodating electrons. Now, there is a specific figure of number of electrons that they can take. And the normal term that is used for it is 2n squared, where n is the shell. That is, either it is the L shell, which is the first shell, or the K shell, which is the first shell, or the L shell, which is the second shell, or the M shell, which is the third shell. Now, if you consider K shell as 1, 2n squared, where n is equal to 1, that means it's 2 times 1 times 1, and the resultant answer is 2. That tells you that the first shell can only accommodate 2 electrons and nothing more. Now, if you go to the second shell, if your n is equal to 2, that means it's going to be 2 times 2 times 2. That is going to give you 8. It means that the second shell can accommodate 8 electrons. Now, if we go to the third shell, that means your n is equal to 3. It's going to be 2 times 3 squared. So that means it's going to be 2 times 3 times 3. That is 18. It means that the third shell is going to accommodate 18 number of electrons. Now, this is what was proposed. And at elementary level, these figures works perfectly well, particularly for the first 20 elements that we have. It can work very, very well. But thereafter, when you go further with elements with higher atomic number, this proposal may not be able to hold. The next thing is that these shells also are now divided into orbitals. You have the s orbital, you have the p orbital, you have the d orbital, and you have the f orbital. The s orbital, which is spherical in nature, can only accommodate 2 electrons. Now the p orbital is divided into 3, the px, py, and pz. Now each of these can only accommodate 2 electrons, and the d orbitals has 5 subdivisions. That is, the d orbital is divided into 5, which means that it can accommodate 10 electrons. And the f orbitals is divided into 7. That means it can accommodate 14 electrons each. Now, there is a rule that guides the admittance of electrons into this orbital. First, you have the Pauline's rule, and secondly, you have the Hooke's rule. The Pauline's rule tries to let us understand that an orbital can only take 2 electrons and nothing more. Each orbital can take 2 electrons and nothing more. That's why we have the s orbital taking 2 electrons. The p orbital, since it's divided into 3, px, py, and pz, each of them taking 2 electrons, that makes it 6 electrons. If you go to the d orbital, that is dx square minus y square, d y square minus z square, and so on. There are 5 of them. And if each of them will take only 2 electrons, that would make a total of 10 electrons. The same thing with the f orbital that can take 14 electrons. Now, Hooke's rule, he now came to make a proposal to explain further that when electrons are going into this orbital, the first thing that happens is that every electron enters singly into the orbital until all the orbitals are occupied. Then the next electron begin to enter into go back to the first, to the second, and to the third orbital. So in other words, each of them will enter into single spin in the orbitals. Take for example, if it's a d orbital, you'll have an electron in the d p orbital px, an electron in the py, and another electron in the pz. That is 1, 1, 1. Now, if there is a 4th electron, that electron will go and pair with the electron in the px. If there is the 5th electron, it will go and pair with the electron in the py orbital. The 6th electron will pair with the electron that is in the pz orbital. Now, that's how Hooke's law is being explained in order to guide the entrance or the admittance of electrons into the orbitals. Now, these laws actually help in explaining the quantum mechanics and quantum rule as far as the energy is concerned. Now, the second thing is that these electrons also have their energies, and they are arranged in accordance with their energies. I wish I have, by next class, I'll be able to come up with maybe a magic board to be able to explain it to you. Or maybe when I have a slide, I can explain it much more better on the slide. You see, the energy of the 1s orbital is less than the energy of the 2s orbital. The energy of the 2s orbital is less than the energy of the 2p orbital. The energy of the 2p orbital is less than the energy of the 3s orbital. The same thing with 3p and 3d. Now, as you move further, you discover that there are some of them that are higher in higher orbital, but their energies are lower. That illustration will be much more better if we have had it on a board, on a screen, so that everybody can see and everyone will be able to follow us and know what I'm actually talking about. Like I promised earlier, by the next class, if I have slide, I'll be able to make these explanations much more better on a slide, and you'll be able to understand it. I wish also some of you that can have access to Concise is in Inorganic Chemistry by J.D. Lee. if you go to Concise Organic Chemistry by J.D. Lee, you will also be able to see those arrangements as they are depicted inside it. It is much more clearer, and it will give you much more about it. So the approximate order of filling of the atomic orbitals goes along the path of the arrow that as they spin through the S, the P, the D, and the F orbital. The principle works very well for the ground state of atoms for the first 18 elements, then increasingly less well for the 100 elements that followed later. The modern form of the above principle describes an order of the orbital energy given by Mendel's rule by stating this: one, that the orbitals are filled in order of increasing energy. Orbitals are filled in order of increasing energy. Two, where two orbitals have the same value of energy, they are filled in order of increasing quantum number n. Where two orbitals have the same value of energy, they are filled in order of increasing quantum number n. That is the principal quantum number. So if you have your biro and you can be able to list the orbitals, first start with 1s on top. Below it, you write 2s and 2p. Go below again, you write 3s, 3p, 3d. You go below, you write 4s, 4p, 4d, 4f. Go down again, enter again, write 5s, 5p, 5d, and 5f. If you try to pass an arrow through the first one, that is the 1s, you pass the second arrow through the 2s. You pass the third arrow through the 2p and 3s. The next arrow is going to go through the 4s, then 3d. So you discover that the energy of the 4s is far, far less than that of the 3d. Now, with this in mind, if we have this, it gives you a better explanation of the periodic table. Now, in the periodic table, if we have seen that also before, the periodic table, which is a chart, and you have it arranged in columns and in row. The periodic table is an arrangement of elements in columns and in row in terms of their increasing atomic number. Now, across the row is what you call the period. Down in the group, that is vertically, is what you call the group. Now, this group actually helps in determining the similarity of the properties of the elements, because each group have the same number of electrons in their atomos shell. For example, if you say group 1, which starts with hydrogen, the next is sodium under it. All of them, as you go down, they all have S1, 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 S1 as an outer electron. And the reactivity of elements actually is determined by the electrons in the atomos shell of the atom. So if they have one S electron, it's expected that their characteristic or their chemical properties will be similar as you go down group 1. The same thing if you go to group 2, which is going to be S2, their properties will also be similar. So all elements along a group have similarities in their chemical properties. And this is so because of the number of electrons that are present in the atomos shell. This electron determines the properties, the way they are released, or the way they combine, that determines the chemical properties of those groups. Now, if you go across horizontally, that's what you call the period. You can have period 1, period 2, period 3, period 4, period 5, period 6, period 7. And as you move down, you are going to find where you will have the lanthanides and the actinides. The lanthanides is named after the element lanthanum. That's why they are called the lanthanides, or they are called the F block elements, or the actinides. It's also named called after actinium, the element actinium. That's why they are called actinides. Now, apart from that classification, which the elements are also labeled in groups, elements are also divided in terms of the orbitals in which electrons are present or where their electrons stop. So you have the S block element, you have the P block element, you have the D block element, and you have the F block elements. That is so because of the electrons that are present in the orbitals of those elements. If, for example, we talk about group 1 and group 2. Group 1 and 2 is when you have S1 and S2. So there are electrons in the S orbital, and that's why they are called S block elements. Now, if you go to the P block elements, that's when electrons begin to enter into the P orbital, and there are also 6 of them. So electron will go into the Px, Py, Pz, if they are 6. So 6 of those electrons will go in. That's why they are called the P block elements. Now, as you move on, electrons will begin to go into the D orbital, and those are the ones they have called the D block elements. They are a separate entity, and they are also looked at differently in terms of the periodic table. When we come to examine those ones, we'll take them separately. We'll take the S block elements, we'll pick the P block elements and study them. We pick the, the D block elements, study their properties, pick the F block element and study their properties. Apart from this naming, or this name that is given to these elements, there are some of them that also share some common names. Like you have the chalcogenes, you have the halogens, and you have the noble gases. Now, one thing we also know about elements is that elements seek for stability. Normally, with an ordinary or elementary understanding of chemistry, is that there are 8 electrons that are involved in the bonding. Now, if elements have fewer electrons, they will prefer to give up those electrons and get bonded with another atom to form a compound. Now, but if they have more, they will prefer to share. Instead of giving, they will prefer to share those electrons in order to form a bond. Now, where you have 4, the energy involved in losing 4 electrons is very high. And the energy involved in accepting 4 electrons is also very, very high. So elements like carbon that falls along that very particular group will prefer to share or to enter into a symbiotic relationship to share their electrons, thereby forming what you call a coordinate bond. The S will give you an electrovalent bond. This one forms the coordinate bond because they share the electrons among themselves. Are you with me? Are you with me?
Yes, we can hear you, sir.
You are with me?
Yes, sir.
Okay, it's all right. So I said the S electrons will prefer to lose, S block elements will prefer to lose electrons in order to form bond, which are called electrovalent bond. Now, those at the extreme end, like the halogens, which have 7 electrons, they will actually prefer to get an element that will share an electron with them. Like if you have like hydrogen and maybe chlorine to form hydrogen chloride. So the chlorine, which has 7 electrons in its atmosphere shell, will find it difficult to lose those 7 electrons. So instead, it will prefer to share that electron with an element that is willing to attach itself to itself, like hydrogen. That's why it forms the hydrogen chloride bond that existed between them. Now, those who have almost equal, like 4 electrons in their atmosphere, they'll prefer to form a coordinate bond. Each one comes with its 4 electrons and they bind together like a symbiotic relationship. So they share that one and they call it a coordinate covalent bond. Now, with this at the back of our mind, it gives us the picture of how the periodic table is like. Now, another thing I failed to mention is about the noble gases. The noble gases have an octet configuration. Octet configuration in the sense that they have 8 electrons in their atmosphere. They don't need to give out, they don't need to receive. Because each element tries to attain that octet configuration. That's why they try to give or to share electrons so that they can have these 8 electrons bounded together. And once they have the 8 electrons bounded together, they are more stable. And that's the state that every element tries to go for or try to look to get to. But the noble gases have 8. So they don't want to give, they don't want to receive. That's why they are not very reactive. They are unreactive. The noble gases always exist as discrete atoms. They are non-reactive. And that is a different characteristic entirely. By the time we begin to also look at that, we'll pick the noble gases and we're going to study them and know what exactly they are. So are you with me? Do you have any question?
For me,
Hello?
I don't have.
Any question?
No, sir.
No, sir.
You say what?
No, sir, I don't have.
You
No
don't
question,
have.
sir.
So now I will ask you then. I will ask you if you cannot ask. Now, can you give me the difference between a shell, a subshell, and an orbiter? A shell, a subshell, and an orbiter. Yes? Rosemary? Rosemary, are you with us?
Yes, sir.
What is a shell?
I didn't start with you before, but nevertheless, let me try. I think the shell is the one that it has a higher energy level, the KLMN. Something like that.
Eh?
I can understand. The KLMN.
Yes, you have the K shell, you have the L shell, you have the M shell. So what is that shell we are talking about? What is it? Yes.
It's a sphere which the energy rotates. That's the electrons rotate through it in different energy level. That's what I didn't start with the class anyway. Just.
But you also have the node. I also expect you to have gone through the node.
I just discovered that the material that I downloaded is different from what you are teaching now. That is what I'm just trying. What I just discovered now.
You didn't download 307?
I downloaded it, but what I'm saying, the material I downloaded is different from what you are teaching now. That is, I'm even somehow confused. So I'm trying to see if I will be able to download it again.
No, if it's 307, chemistry 307 is the same chemistry that I am teaching now. It may not.
Yes, sir, but the chemistry 307 that I have now, the first topic is Schrodinger
equation. No,
yes, that's the first topic.
There's something is wrong with that one.
That is what I'm trying to say now.
Uh,
The first one is Schrodinger equation. The second one is theories of bonding. So
no,
when I started listening to the class, it's like I was confused.
no,
I was trying to go through the material.
no, something is wrong with that one. If you start with Schrodinger's equation.
So that is why I'm really, really confused. Because
Uh,
I've gone far. But I was surprised that when I was listening, the topic was so different from what is in the material. So I will try and see if I can re-download again. So to get the real material.
if you go to my environment, you go to my learning.
Yes,
if you go to my learning environment, I think I tried to drop it there.
Yes, I saw it now. That is when I went there. I said, well, teacher, I have to go through there. So when I saw it, I discovered that the topics are different from what I have. So I have to look for a way I would re-download so I'll be able to go through it again, sir.
It's all right. So, Michael, can you help us? What is an orbital? Michael? Michael Aka, are you with us?
I'm with you, sir.
I said, what is a subshell?
Okay, an orbital.
Okay, an orbital.
A subshell has to do with a set of states. A set of states in a shell. You know, it's usually defined by this the XP, the azimuthal quantum number.
Correct. It has to do. It's common with the azimuthal quantum number.
Exactly.
And it also tried to give us the number of electrons that are actually present in it. Now, can Adamu Joseph, can you tell me what is an orbital? Adamu Joseph. Adamu Joseph, are you with us? Is Adamu Joseph with us? Okay, so let's go ahead with what we have before us. Now, I have some few questions here which I would want to drop along with you, so that by the time we come to the next class, you should have tried to understand some of those basic things. If you open to the course outline on page 9, the course content, on page 9, you will see some self-assessment question there, and you see 6.0, there are tutor marked assignment. Tutor marked assignment. So take the self-assessment questions and try to answer them and understand them properly. And those were some of the questions that I asked you. Define and distinguish between the shell, subshell, and orbital. And 2, explain the relationship between the quantum numbers. Explain the relationship between the quantum numbers. Now, in summary, if you try, or you might have understood what we have tried to do today, or if you have a paper with you, you try to take note. 1, we talk about the electronic configuration, which refers to the arrangement of electrons as they revolve around the nuclei of an atom. So it may be 1 electron, it may be 2 electrons, but as long as they revolve around the nuclei of an atom, that is the arrangement of the electrons. And energy is associated with each movement of the electron. Now, first, where the elements are inactive, you consider that as the ground state of the element. At that time, no energy has been added, or they have not absorbed any energy. Where energy is added, they become excited, and you call that one excited state. Most of the activity of the element or of the atom takes place at the excited state, when they are excited. That is when the electron is ready to be released or to be absorbed in. And that is when bonds are actually formed. So most activity of atoms or elements takes place at the excited state. This we must know. Now, the molecular orbitals are also labeled according to their symmetry. rather than according to their atomic levels, which are normally used in either monoatomic atoms or diatomic atoms. And as I told you earlier, that the S is spherical, the P are two dumbbell structures. The P are dumbbell structures. The D are a little bit more complex, but if you, I don't know, there was one recorded lesson which I posted on the learning in my learning environment. Did you see it, Michael? Michael, are you with me?
I find it difficult accessing that environment, sir.
Okay, you find it difficult getting to my learning environment?
Yes, sir.
But there is a PowerPoint lecture that I dropped there. Now, if you are able, you saw it?
I saw it, but I didn't open it.
Yes, when you open it, some of these structures of the S, the P, the D, you'll see it in the PowerPoint there. You'll see, you will see them there, the structures and the way they are written. And I also try to explain in that 7 minutes lecture. I try to make some explanation on them there. And there is also the periodic table, which I also dropped there in one of the slides. So if you are able to go through that, it's like a summary of actually what I am telling you today. Some of those things that I told you I would have loved to have been to do the illustration on the board. You will see them on the slide there. And the energies of the orbital I talk about and the arrows that goes through them, they are also on a slide in that very particular lecture. I wish all of you should actually try to have access to it. When you get it, you'll be able to comprehend what I'm telling you actually much more better. So if you have a question, you can ask me. If you have no question, we may actually stop here since we are not very much. I think we are supposed to be 23 in this class, but I have only 3 of you. So by next class, I will try to send the message very early enough and repeat it on and on so that a lot of people will come to attend. Meanwhile, before this time, Rosemary, are you with me?
Yes,
Rosemary,
sir.
we were actually discussing with Michael about a convenient time. What is your opinion?
Most of the evenings are okay with me anyway, sir. Evenings are okay with me. Especially Fridays.
But we are saying that the poor attendance today may be as a result of the Ramadan period. Some of our brothers that are Muslim, they may be breaking their fast by now. Maybe that's why they couldn't turn up for the class.
So are you, what time are you thinking of putting it on, sir?
I wouldn't mind any other day, maybe from 9 to 10 or 10 to 11 or 11
okay, no problem, sir.
In working days.
I can make time for it, sir.
Eh?
I can make time for it, sir.
Michael, can you also do the same?
For a working day, I will not be available.
Working days, you won't be available?
Yeah, in the morning and afternoon hours.
Oh, except if it is late in the evening.
Evenings are okay by me.
Okay, fine. I will tinker around and see how we can adjust some of those classes, either to evening or take it around Saturday morning hours.
Okay, I think Saturday is okay. It's also better.
Okay, it's all right. So what's more?
Or if I may suggest,
yeah.
Sir, if I may suggest, I think because I got this invitation evening, that's yesterday's evening.
Yes.
The time may also contribute to the poor attendance. So if, like you said, you send it earlier and put up reminders again, I believe that may also increase the participation. Possibly we can give a shot again at this Friday evening and see what next week will turn out to be.
Okay. It's all right. Maybe what will happen is that by by Sunday, I'll begin to send out the notices. And
Okay, sir.
I'll make sure there is a gap of around maybe 2 days, and also send reminders to see if the participation will increase. So you are welcome on board. Thank you very much for coming. I wish you good rest tonight. Thank you.
Thank you so much.
Thank you very much,
Have a
sir.
great day too.
Thank you.